the reason we want to do these is we want to be able to simplify them, rewrite them in another way. Some of that is for use in calculus later on. I mean, same reason we do some of the algebra. I mean, you learn some of the algebra techniques of rearranging and rewriting and simplifying things so you could apply it to these functions as well. And then in calculus, matter of fact, one of the things we're working on right now in calculus is called antiderivatives or integrals that we're working on. And to be able to do those, oftentimes we have to make them look a certain way, right? How they look or what their kind of arrangement of terms is determines how we approach the problem. And by rearranging them or changing them using an identity like these, it can help us do the problem. It can make it simple. Okay, and so that is the value that we have in doing these. But these are called identities on that cheat sheet. Matter of fact, get out that cheat sheet real quick that I gave you. On that cheat sheet, these are called, that section, the thing you highlighted, they're all called identities, right? Except, I guess, the co-functions say co-function formulas, and the even odd say formulas, but they're really identities. What that means is the left side is identical to the right side. They're equal. That's why we use the word identity. And so what that means when you're doing these problems is every step along the way as you're simplifying, you're taking something and rewriting it into an equivalent form. And so your second step is identical to the first step, and your third step is identical to the second step, and your final step is identical to all the other steps before it. And that's why then in calculus we can use that. We can rewrite it in an identical form to be able to then do some calculus work with it, okay? So there's a lot of different ways we might want to do it. Sometimes the directions are just simplify. Sometimes the directions are turn this one, like what you did here in the beginning, turn this one into this one. And then the kind of the new one here, which we were just talking about, this section here says write it in terms of sign. What does that mean? At the end, your answer has to only have sign in it. Now, it could be a sign squared, it could have a 2 plus sign, but it can't have any other trig functions in it. So in terms of sign means it can only have sign in it, nothing else. And again, in calculus, there might be some advantages, or other higher math classes, there might be some advantages to being just in sign and not any other trig functions. That is the purpose, okay? So let's talk about a few of these. So on number 1, okay, for example, we're supposed to turn it into that. Well, negative tangent, we probably write that as negative sine over cosine. We take that times cosine, the cosines cancel. We get negative sine theta. Here's where it would be important to put that back into theta, but we know, hopefully, that since it's an odd function, one of our formulas is that if we put, a negative inside, that's the same as having a negative outside. And that's true for cosecant, that's true for tangent, that's true for cotangent. And then for cosine and secant, it's negative on the inside, the same as not having a negative at all, anywhere. We can just kind of get rid of it. So we do that, leads us to that, which leads us to that, and that's what we want to end up with. Okay, so obviously there must be some questions on these down here. Is that what I'm hearing? Okay, all right, now, before we get into that, I've got some stuff written on the board over here that I want to talk about. This came up this morning, and I did kind of probably just kind of gloss over this without thinking too much about it, whether there might be some questions about this, and then the question came up, and I thought, yes, we should talk about it. So there's a couple of algebra things that we need to talk about here with squaring. If you have a fraction squared, it's okay to square the top, square the bottom. Right? That's one of the laws of exponents. And so a squared over b squared. Now that applies to this over here then. So since tangent we know is sine over cosine, it makes sense then that if you square tangent, that'd be the same as squaring this fraction. And if you square this fraction, you can square the top, square the bottom. So tangent is sine over cosine. That means that tangent squared, yes, is sine squared over cosine squared. Tangent cubed would be sine cubed over cosine cubed. Tangent to the fourth would be sine to the fourth over cosine to the fourth, right? Everybody okay with that? All right, same thing with the reciprocal identities. 1 over sine is equal to cosecant. Well, if you square this fraction, you can square the top, which would still be 1, and square the bottom, which is sine squared, and then that should be equal to cosecant squared. So 1 over sine is cosecant, 1 over sine squared is cosecant squared, 1 over sine cubed is cosecant cubed, and so forth. So all the reciprocal identities, and these two with tangent and cotangent, we can put that into square. However, that doesn't apply to the Pythagorean identities. It is not true in algebra that if you have a plus b and you square it, that that's a squared plus b squared. That doesn't work. That's a FOIL, and you cannot do that. So therefore, it is not true, since sine squared plus cosine squared equals 1, it is not true that sine plus cosine would equal 1. The Pythagorean identities, and we're going to do an activity with those today, the ones that say tangent squared plus 1 is secant squared, and cotangent squared plus 1 is cosecant squared, those have to be squared. They can't be cubed, they can't be any other power, they have to be squared. Okay? That's the only way you can use those. 1 minus cosine squared is sine squared. That doesn't mean that 1 minus cosine is sine. It doesn't work that way. So the Pythagorean identities have to be with squareds, okay? But these can be squared, cubed, whatever. Okay? All right. So I thought that was maybe important to say. Maybe we weren't mixed up about that, but in case you were. All right, let's talk about this one. This one is a plus. We need to get common denominators. So you can think bow tie if you want. Okay, that's actually a really nice one to bow tie, just this times this. But basically you're just saying, okay, the top is going to be 1 minus cotangent on this one. The top on this one's going to be 1 plus cotangent. All right, and then your common denominator is going to be those two together. Now, I know I did just kind of show some work there that you might not be real comfortable with, so maybe we should come over here and do that a little nicer. So what was this? This was 1 plus cotangent here, and then this was plus, and this was 1 minus cotangent. Okay, so what am I doing? I'm going to say, okay, I'm going to take this one times 1 plus cotangent. The other day, a lot of you were saying you like getting common denominators better than the bow tie. I'm fine with that, but it would look like this then. We're going to take the top bottom times 1 minus cotangent. The reason you get common denominators is so you can add the tops. The reason you get common denominators is so that you can add the tops. 2 sevenths plus 3 sevenths is 5 sevenths. We add the tops, we keep our common denominator. So this is going to be 1 minus cotangent plus 1 plus cotangent, and then our common denominator is going to be these two together. Now I know I said a lot of times we don't multiply those together. However, in this case, I think we are going to want to multiply those together. Well, let's see. Wait a minute. Yes, we are going to want to multiply those together. Okay, and what do we get? We get 1 minus cotangent squared. Okay, all right. Now, the cotangents cancel, right, like that. And so what do we get? We get 2 over 1 minus cotangent squared. Now, not only is it a good idea to come over here, because I really don't think on most of these worksheets we do, unless you write teeny tiny, I don't think you're doing the work on the worksheet, probably on your own paper, right? I think some of these take quite a bit of work. If you're trying to squeeze it all into on the worksheet, you know, then you're probably going to mess something up, and it's going to be hard to do. Okay, so I would recommend doing it on other paper anyway. Okay, now what was the directions here though? Get it in terms of sign. Now sometimes the directions might have been write it so it's not a fraction, or write it you know, in terms of sines and cosines, or whatever, right? I mean, so if it just says simplify, it's always kind of hard to know where to stop. I mean, you might argue that this is, we've put the two fractions together into one fraction. Sometimes that's all we want, right? Okay, and so I'm probably going to avoid giving you a bunch of problems on a quiz where it just says simplify, right? Because then it's a little fuzzy on how far do you need to go. That's why I like, you know, put it in terms of sign or do an identity. You know, you got to make this look like this. So and then I can check your work to see if you're getting it, okay? So anyway, let's keep going. So now the problem is if you go to your trig identities, your Pythagorean identities, don't you have this one here? Isn't that one right there? Well, that doesn't quite work, does it? There's no way I can turn this into 1 minus. There's no way, I can't take out a negative, because if I do, these are both going to turn negative. So I cannot turn a plus into a minus like that. So that's unfortunate. So probably what I need to do is what? What's my goal here anyway? Get it in terms of sine, right? And so probably it's time to make this cosine over sine. So I'm going to go ahead and do that. And so I'm going to make this as cosine squared over sine squared. Okay? All right, so now I got that. All right, so now what can I do with that bottom? What do I need to do with that bottom? What do I need to do with this right here? No. And the reason we can't do that is because of this minus here. I can't just flip this up here because of multiple terms here. If it was just 2 over this, I could.
Was it 1 over 1 minus?
Yes, I need to get that as a common denominator. I need to look at this and think, okay, this is 1 over 1. So what can I do to this 1 over 1? So I need this to be sine squared over sine squared. I need a fancy 1, right? I need a fancy 1 here. So I need sine squared over sine squared, because then I can do what you wanted to do. See, now when I put those together, now I can flip this up. See, so now I got 2 over, now what do I have here? I got sine squared minus cosine squared all over sine squared. Okay, now I can flip that. Yeah, what'd I do there?
Why were you able to turn that
Into sine squared over sine squared? It's like turning 1 into 6 over 6 or 7 over 7 or 8 over 8. I didn't turn it into sine squared. I turned it into sine squared over sine squared, which is 1. And the reason I wanted to do that is I wanted a common denominator, right? The only way to put 1 minus a fraction together, it's kind of like having 1 minus 3/4. I need to turn the 1 into 4/4, right? I need to do 4/4 minus 3/4 so I can put it together. That's what I'm doing, right? That's what I'm doing, okay? All right, so now I can flip this, right? So I can flip this up here, and now I got sine squared on top, and I got sine squared minus cosine squared on the bottom, right? So the 2 is going to be on top of that, so I'm going to go to a new page here. So I got 2 sine squared over, and what was it? Sine squared minus cosine squared, right? I got that right there. Okay, now, again, we got to think about what the goal is. So what my strategies here are different than they might have been if it was just to simplify, or if it was just to turn it into sine cosine. My goal here is to get it just in terms of sine. So I'm close. I got that dumb cosine squared in there, but wait a minute, what's cosine squared equal to? 1 minus sine squared, right? Look at your Pythagorean identities again. Cosine squared, we use those a ton, especially when you get a problem that's got squares in it. You get a problem that's got cotangent squares and tangent squares, you can turn those into sine squares and cosine squares. We got a Pythagorean identity right here. So anytime you got that sine squared and cosine squared, you want to really be on the lookout for those variations that you can use. So what I'm going to do here, now you got to be careful with your negatives and stuff, but this is going to be 2 sine squared, and then this is going to be sine squared minus, now I need parentheses, and I'm going to replace that with a 1 minus sine squared, like that. Now, why do I have to be so careful with that parenthesis? Because some people might look at that and say, oh, good, the sine squareds will cancel. No, they don't, right? Because what do you got here? This is minus 1. This is like plus. That turns to negative. That turns to positive. So we end up with 2 sine squared over what? 2 sine squared minus 1. And there's your final answer. As much as you're tempted and want to cancel these sine squareds, you can't because of that plus and that minus in there. You can't do it. I mean, it's just like having x over x plus 3. You can't cancel those x's, right? That doesn't work. You can't do it, okay? So, you just, I mean, it'd sure be nice. It looks like maybe we could. A lot of problems we can manipulate it so that some things cancel. Turns out we can't. So that one's just getting it turned into sines and cosines. Okay, or I'm sorry, just sines. Okay, now you contrast that with the next one. That's one thing about, whoops, there you go. There's a little calculus. Well, it does look awful. You're right, but you've never seen it before. Come on. Look at What would you have thought of this last year in Algebra 2 class, right? You'd have thought that was a mess too. Well, maybe you still do. Maybe you do right now. All right. Yeah, that's true. Maybe you do. All right, but let's see, what was I doing? Okay, here. So sometimes you get one, and it does get to be messy. It doesn't necessarily look like, well, maybe this one did look like it was going to be, but then this one's really nice. I mean, this one's cosine squared over sine squared times your sine squared. So your sine squareds cancel, and then you're supposed to, but it's cosine squared, but you're supposed to have in terms of sine, so what's cosine squared? 1 minus sine squared. And so you just, and that's it. I mean, so you contrast that to this one. This one was kind of a real mess. Had to get common denominators twice. Okay? This one, they just canceled, and then you did it. There you go. And that happens. I mean, one is just awful, and then all of a sudden the next one's not bad at all. Okay? Some more in here in the middle? 6, 7? All of them?
Yes.
Okay, well, I don't do all of them, but yes. Okay?
11, yes.
All right.
Maybe even the back door too.
And, did you do the back? Oh. All right. So, see, so now this one we're supposed to get in terms of cosine, right? So 1 over cosine squared. Let me see how messy it is before I decide if I need to go to the back here. Sine squared, which would just be over 1, and then minus sine squared over cosine squared, like that, right? So secant squared is 1 over cosine squared, sine squared is just that, and then tangent squared is sine squared over cosine squared. So now, you got 2 of them that already have common denominators. So I would just go ahead and put those together. All we have to do is get it in terms of cosine. So I'm not sure we need to get all 3 of them added together, right? I think maybe we can just do these 2 and see what happens. So I'm going to take this one and this one and put them together. Now that's going to be 1 minus sine squared over cosine squared. And then this one's just kind of hanging out here by itself. Okay, that one's got a different denominator. I can't put that together. But these 2 I can. So we can just add the tops, which would be 1 minus sine squared over the common denominator, cosine squared. Oh, that's a really nice one, because what's 1 minus sine squared? Cosine squared, and cosine squared over cosine squared is 1. So this whole thing is now 1. See why this is not going to work for you on your worksheet. But anyway, so this whole thing is just 1 minus sine squared. Right? This is 1. So this whole thing here is 1. 1 minus sine squared is cosine squared. So your final answer is,
Wow, of course. I did like half a page of work.
half. Well, you can do that. I mean, you can, like, I use an analogy. You're trying to get to Walmart from here. There's a lot of ways to go. And some of them are really long, and you go a lot of, wrong turns and back up, and you get there, but it's maybe not the quickest. So don't think you'll always see the quickest route. I could have gotten this with common denominators and done some things, and it might have looked a little different, but at the end of the day, it should have simplified down to that. Okay? All right, what about this one? What are you thinking when you see this one here? Factor. This is a FOIL. When you see a sine to the 4th and a sine squared and then nothing in there, that's going to be a FOIL problem. And it turns out it's actually a nice one. It's just sine squared minus 1 and sine squared minus 1. Okay? Now, those look familiar, but they're not quite what I want them to be. What do I want those to be? I want those to be 1 minus sine squared, okay, which I actually can do. If I take a negative out of this one, that turns negative, that turns positive, that makes it 1 minus sine squared, and then take a negative out of the other one. Well, if you take 2 negatives out, what happens? They're positive. So this actually is the same as this, where they're both 1 minus sine squared. Well, that actually makes sense, because if you had negative 5 times negative 5, that's 25. That's the same as taking out 2 negatives, and 5 times 5 is also 25. So that's what we just did right there. Well, what's that? That's cosine squared times cosine squared, which is cosine to the 4. So the whole thing is just cosine to the 4. Okay? All right. This one is very, very much like number 4, so I'm going to let you do that one on your own. I'm not going to go through that one. I'm going to let you do it. You can do it. You've seen number 4 now, so now you can go through what we just did on number 4. You get a common denominator, and you can see what happens. And you want to get it in terms of tangent, okay? Now, let's do number 9, though. Okay? Number 9 is a little more interesting, okay? Because you're trying to get in terms of tangent, and the only connection you have with tangent is sine over cosine. So how are we going to get that? Well, so we can take this and we can make this be 1 over, we can move that cosine to the bottom. So we can make this be cosine times sine, right? 1 over cosine, and then the sine's already down there. There's no plus sign, so that's why it's okay to just flip that down there. There's nothing being added or anything like that. Okay? Now, how in the world can we get this in terms of tangent? What do you think? Say that again.
So, 1 over cosine and that's over sine. You want to leave it up.
You could. Well, let's do that. Yeah, that would be the same thing. So secant is 1 over cosine, and then all over sine. Okay, you can do that. But I guess my thinking on that is what is the advantage of that? I mean, we can. Flip the sign up, which is 1 over sine, right, like that. So then you end up with what I had earlier, right, which you just, it's fine, I mean, that's okay, but I'm just, yes, you would flip the sign up. Now, my fear is what you're thinking is you flip the sign up and it'll go on top. Yeah, see, and it wouldn't, because this is sine on the bottom, so to flip it, it'd be 1 over sine. Right, that's the problem. If you just take this sign and put it up there, then that's different than flipping it.
Keep it like we had it before.
Okay. Well, you're right, because when I look at this and I see what I have here, okay, I'm looking at this, I'm thinking, well, this is a long ways from a tangent. I need like a sine over cosine. So this would be that example of kind of going down a road that maybe we don't want to go down. And so then let's look at it again, and let's see the secant. Maybe that's a hint. What identity do we have that relates secant with tangent? Tangent squared plus 1 equals secant squared. So now I'm thinking, how can I get a secant squared? Well, I can multiply the top and bottom by secant. Again, that's just a fancy 1. So multiply the top and bottom by secant, because then that's going to give me secant squared, and then this is going to give me sine times secant. Well, what's sine times secant? Well, let's just write it. Let's just write it because we're not seeing it right away. That's fine. Yeah, see, so what is the top now? The top is the same as 1 plus tangent squared, right? Because that's secant squared. And now sine times secant, isn't that the same as sine times 1 over cosine? Isn't that just sine over cosine? Which is tangent. So the bottom actually just turns into tangent. That was kind of a free one, because we were trying to get secant squared, and while doing so, it ended up making the bottom for cosine. Okay? So that's, again, sometimes it is. It's a little bit of creativity. It's a little bit of guess and check. It's a little bit of, okay, this looks like one I've done before, hopefully. So the more of them you do, the things will start to come to you a little bit. Okay? All right. So, I mean, this one is just show that this can be converted into this, right? Well, that just means cosine cubed. You look at what they did. What is that right there? Cosine squared. So all they did is they took cosine cubed and made it cosine squared times cosine. And then they turned the cosine squared into 1 minus sine squared, and then left the cosine, and then left the sine to the fourth. And then that's that right there. So they just broke apart the cosine cubed and did that to it. Now, again, you guys don't believe me. Let me show you another ugly one here from calculus class. Oh, shoot. No, I don't think I have it. Darn it. Wait, I might. No. Right here. Look what we did on this problem. This x cubed right here, we took it and we said, let's don't think of that as x cubed, let's think of it as x squared times x, right? Because then we can do something with the x squared and we can do something different with the x. Well, that's You guys are missing out. You guys that didn't sign up. I feel bad for you. Feel bad. You're gonna miss out on that. Well, look at our problems. Look at our problems.
Which way choose, that's the answer.
Look at our problems. There's no numbers there. Well, there is a 2 there. I guess there's a 2 in there. Otherwise, that's the only number in the problem. Okay. So anyway, that's what we were saying. And that was the same strategy we just applied there. We took cosine cubed and thought it was cosine squared times a cosine. Because we knew the cosine squared we could turn into 1 minus sine squared. All right. And then this one's pretty easy too. This one's just a matter of taking the cotangent squared plus the 1, right? Cotangent squared plus the 1 is the same as what? Secant squared. So now you got a secant squared plus a secant squared. You got 2 secant squared over a cotangent squared. Right? Did I do that right? Why does that not seem right? Isn't a cotangent squared plus 1? It's cosecant squared. That's right. Cosecant squared. Okay, so that's cosecant squared. Yeah, you're right. Cosecant squared plus secant squared over cotangent squared. Okay. Yeah, I'm seeing if there's a simple way. I know where we're going to go next, but I'm seeing if there's a simple way. Okay, doesn't look like. So now we're going to split this apart. Okay, so now we're going to get cosecant squared over cotangent squared, and at least I'm not seeing it right now. And then this is secant squared over cotangent squared. Okay, now what's cosecant squared over cotangent squared? We can flip those around, right? Cosecant squared is 1 over sine squared, and cotangent squared is cosine squared over sine squared, right? And so we can flip that. And we get sine squared over cosine squared. Sine squareds cancel. So we get 1 over cosine squared, which would be secant squared. So this whole thing is just secant squared. Isn't it? Yeah. 1 over cosine squared. I just flip that. Sine squareds cancel. For some reason, when I did this earlier, it seemed a lot simpler. And now this one's not as nice. Secant squared would be 1 over cosine squared. And then that's cosine squared over sine squared. When we flip that one, we're going to get sine squared over cosine squared. So that's sine squared over cosine to the 4th. Oh yeah, that's actually going to work. So secant squared. So this one, we got secant squared. Now I just realized I'm going to leave that 1 over cosine squared. Okay. I'm going to leave that 1 over cosine squared right here. And then this one, I just am doing over here. And what do I get here? I get sine squared plus cosine to the 4th. Right? So, because nothing cancels here when I flip this one. So I get sine squared over cosine to the 4th. Now, what do I have to do to add these together? I need a common denominator. So I need a cosine squared and a cosine squared here to turn this into cosine to the 4th. Now, what do I get on top? I get cosine squared plus sine squared. See, I love that. I love the sound of that. Oh, yes. Yes! That's what you were going to follow with, Charlie, right? Was it, oh, yeah, right. Yes. Cosine squared plus sine squared is 1. And then cosine to the 4th is our common denominator. Cosine to the 4th, 1 over cosine to the 4th is secant to the 4th. Awesome. Love it. That is so fun. All right. Good stuff. All right. So these, we're going to get a little practice on these bottom ones here, so we're not going to do it right now. We got some things to do. Let's see. Yeah, let's do this. Let's go to the back. Let's go to the back. Okay? 20 minutes. Work on the back. Okay? You can work together if you want. Yes. Okay? work on the back. Work on the back. Okay?
You get cosine plus sine, cosine squared plus sine squared.
No, these two. These two.
And then we're doing
That was easy. See, I'm a genius. Cosecant is just
What do they want? Like, do they want this?
So you have a formula for changes to our.
Do you want to get this to this, or do you want to get this to this?
What's that now?
So then you just write one.
What is this big one? Like, do we have to try to work out how to do this? Or do we?
So you have cosecant squared out.
I gotta do this.
Oh,
I agree.
I
feel like we have limited options.
Well, yeah, because you really So, yeah. I tell you what, let's do this. On the problems where it says, convert the first expression into the second expression, I will let you go either direction. Actually, you can work. Another way of doing the same problem is to, it says verify the identity. In other words, verify that the left side is equal to the right side. And you can do that actually by working with both sides. So in other words, if I gave you this problem here, if I gave you this problem right here and said verify that the left side is equal to the right side, a lot of times what we do is we put like a line there. I call it a T-chart sometimes because that kind of makes a T there in the problem. And verify means show that the two sides are equal. Now you can't add things across. You can't do like you're solving. You can't move things across. But what you can do is you can simplify this side and say, well, that equals that. And this side would equal that. And then you'd be like, yeah, okay, check. They are the same. So I'll let you do that. You can work with the right side if you want to make it look like the left, You can work with the left, make it look like the right, or you can work with both sides and show that they end up being the same. Just make sure you don't add things across or move things from side to side. You can't do that.
That would be.
Yeah, I know. But that's why you want to write.